Okay, let's go.
By using ANSYS Workbench 2023 R2, we can use computational fluid dynamics or CFD. CFD is used to simulate fluid flow and heat transfer. For example, it can design a more aerodynamic car using CFD simulate. It also can simulate airflow around the car, help engineers optimize its shape for reduced drag and improve fuel efficiency.
Hanif, can you tell me one related theory about our project?
The related of this project is aerodynamic cars. It has three main points about aerodynamic cars. First is streamlined shape. Aerodynamic cars features sleek and streamlined design to minimize air resistance and drag. Smooth curve exterior reduce turbulence, allowing the vehicle to move through the air with less resistance. Second is aerodynamic components. Cars are equipped with specialized components like spoilers, diffuser, and underbody panels to manage airflow. The last one is wind tunnel testing. Engineers use wind tunnel for meticulous testing of a car's aerodynamics. These tests help fine-tune design by analyzing airflow pattern, pressure point, and drag coefficient, ensuring optimal aerodynamic performance.
And what is the main problem that we need to solve during this simulation for the CFD project?
The problem that need to be solved in this simulation is to identify the key parameters and variables that play a role in the fluid flow problem. Second, simulation setup. Develop an accurate 3D geometry of the system under consideration. Set up appropriate boundary conditions, specifying the behavior at inlet, outlet, walls, and other relevant boundaries. Generate a mesh that discretize the geometry, paying attention to mesh quality and refinement in critical areas. Choose an appropriate solver, numerical setting, and turbulence model based on the physics of the problem. The last one is analysis and interpretation. Run the simulation, monitor convergence, and analyze the result. Post-process the simulation data to generate visualization such as contour plot, velocity vectors, and pressure distribution. Interpret the result in the context of the problem, identifying key flow patterns, area of interest, and insight gain. And iterate on the simulation setup if needed, and document the process the result for reproducibility and future reference.
Farish, if there any setting or method simulation before doing meshing? Okay, Hanif. To handle the geometry and dimension, we must include the three main points. The first is geometry import. Import a 3D CAD model or create a geometry representation of the system you want to simulate. The geometry should include all relevant components and features that affect the airflow. And also, you must ensure the geometry is close and watertight to avoid issues during meshing. Second one is you must to detail about scale and units. Ensure that the dimension of your geometry are defined accurately in appropriate units like meters, millimeters and others. And verify that the scale of the geometry correspond to the real world scale of the physical system. And lastly is geometrical change. If you studying the impact of geometric variation or on airflow, consider making parametric change to the geometry. This can involve altering dimension or shape to analyze how different configuration affect the flow.
What the meaning of meshing? Can you describe about it?
Oh, about meshing. For your information, meshing is the process of dividing the computational domain into smaller elements to the descriptive the geometry for the numerical analysis. Oh, talking about setting or simulation method, we are dividing to 4 points. First point is geometry import, pre-processing, mesh generation, and quality check. And also about method simulation, it also dividing with 2 points, which is inlet and outlet boundary condition. For the method of inlet boundary condition, it specify the velocity, pressure, or mass flow rate at the inlet based on your problem. Define the turbulence parameter if the flow is expected to be turbulent. Consider adding any addition properties like temperature or species concentration. And then for the outlet, you can either specify a static pressure, mass flow rate, or allow the software to calculate the outlet pressure based on the flow condition, and ensure that the outlet condition do not cause backflow or recirculation and the domain is the well post. I forgot about emulation run. Emulation run is the run the simulation and monitor convergence. The method is for the run simulation is execute the simulation and monitor convergence. We adjust the setting as needed, and other than that is a post-processing. Post-process is the result using visualization tools to analyze velocity profile, pressure distribution, and other relevant parameters. Aiman, your part is set up, right? So, what the step you do to do the setup?
First of all, click General and check the mesh twice. Then click the report quality to gain the result of mesh quality. Then choose lamina and viscose models. Go to the material, select air and change the density to 1 and viscosity to 1 exponent -4. At cell zone, choose air. Then boundary condition. At 4 feet pressure, choose type symmetry.
Okay, so it is enough step for the setup.
No, there are 3 or more steps. First of all, go to the residual at monitor. Insert 0.000001 for continuity, x velocity and y velocity. Second step, go to the initialization, insert 1 and 2 at x velocity and y velocity. Then, run calculation. Insert 1 million at number of iterations and calculate. Then, it will show a graph with the data already calculated. Go to the residual monitor, change 1 exponent -7 at absolute criteria, then run calculation. So, that's all for setup and solution.
Okay, Aiman, the last part is getting the result. So, what you do to get the result?
To get the result, first, we must select contour and choose velocity at section contour off. Then, it will show a colorful rectangle with their own magnitude. Then, click vectors and save. It will show an arrow of velocity. Next, at pass lines, for release from surface section, choose inlet and save. Next, at detail contour 1 of CFD post, select symmetry 2 in location and insert 50 at hashtag of contour. Then change the variable from pressure to velocity. After that, click chart. At their details, they have x-axis and y-axis. For x-axis, the variable are velocity and y-axis are y. For the last step, click insert. Then click location and click line 1. At their details, insert 0.15 meter at point 1 and 0.75 meter at point 2. Go to detail of chart 1, choose location line 1 at data series. Choose velocity u at x-axis and choose y at y-axis. So the graph will generate. So that's all, the whole step for result. Thank you.
Okay, Hakim. Your part is result. Can you explain to us about your result?
Okay, from the velocity, the result that I conclude is in the middle of the duct, the velocity profile shows a relatively uniform flow with a maximum velocity at the center line. The flow is mostly laminar and there are no significant vortices present. Okay, for the aspect of pressure, what can I conclude is the pressure distribution in the middle section shows a balanced profile with a slight pressure drop along the length of the duct. High pressure regions are concentrated near the inlet, while lower pressures are observed as the air progresses towards the middle. The other aspect that I conclude in the result is line of plot. The flow in the middle is characterized by a stable and well-defined laminar pattern. The boundary layers remains attached to the walls without significant separation.
Okay, Hakim. We saw the flow have a different. So, can you tell us the effect from velocity profile and thickness?
Okay, the effect from velocity profile and thickness, we can relate with the simple explanation. When the thickness are high, pressure also high, and their velocity are low. Then, when the thickness are low, pressure also low, and their velocity are high. For the simple example, stone in the water. When the thickness of stone are high, the pressure of water are high, and the flow of water, which is their velocity, are low.